On a mountain in the Canary Islands, 2 telescopes spend their nights taking orders from light that left its source before the Earth existed. They are pointed at quasars, the burning cores of galaxies so distant that this light has been travelling for 7.8 billion years, and that ancient light is being used in real time to decide which question a physics experiment will ask. It sounds like a piece of theatre. It is not. It is the last move in a campaign that ran for more than 50 years, and the thing those machines were built to test was not a particle or a force. It was you. It was whether the person standing at the apparatus could have chosen anything else. So what happens when physics runs an experiment on free will itself? By the end of tonight, you will know exactly what those machines proved, exactly what they could never touch, and why the answer unsettled the people who found it. Get comfortable and let the room go quiet around you. Subscribe if you have not already, and stay with us, because the thing that stopped this experiment cold is not a piece of missing equipment. It is something much closer to home. Let's begin. Part 1. The question that was not physics. In the spring of 1935, 3 men published 4 pages that a great many physicists wished they had not written. The paper appeared in Physical Review, and it carried a question in its title rather than a claim. Can quantum mechanical description of physical reality be considered complete? That was the whole title. It reads less like a scientific paper and more like something muttered at the end of a long argument, which, in a sense, is exactly what it was. The 3 names on it were Albert Einstein, Boris Podolsky, and Nathan Rosen, and for the rest of the century people would refer to it simply by their initials. Their answer to their own question was no. I want to be careful here, because this is the part that gets garbled almost every single time the story is told. Einstein was not saying quantum mechanics was wrong. He never said that. He had helped build the thing. He had won a Nobel Prize for work that sits at its foundation. What he was saying was subtler, and if anything, more damaging. He was saying it was unfinished. He was saying that the theory worked beautifully, made correct predictions, and was nevertheless leaving something out. That underneath the probabilities there had to be something more solid, some set of properties the theory had simply failed to write down. The argument they built to make that case is the reason we're here tonight, roughly 90 years later, talking about telescopes on a mountain in the Canary Islands. Picture 2 particles created together in a single event, born out of the same interaction, and then allowed to fly apart. They travel in opposite directions. One goes left, one goes right. You can let them travel as far as you like, across a room, across a country, across a solar system. Quantum mechanics says that under the right conditions those 2 particles remain connected in a specific mathematical sense, and that when you measure a property of the one on the left, the corresponding property of the one on the right is fixed in the same instant, not eventually, not after a signal has time to cross the gap, instantly. Einstein found that intolerable, and he had an extremely good reason. He had spent the previous 30 years establishing that nothing in the universe outruns light. The idea that a measurement in one place could immediately settle a matter in another place, arbitrarily far away, looked to him like a violation of everything he had built. He wrote about it years later, in a letter to his friend Max Born, using a German phrase that has followed the subject around ever since, spukhafte Fernwirkung, spooky action at a distance. And notice that he used the word spooky, which is not a compliment in any language. He meant it the way you would mean it about a house where the lights turn themselves on. So Einstein proposed the sensible alternative, the one that any reasonable person would propose. There is no instantaneous connection, he said. The particles simply left the factory with their answers already printed on them. When you measure the left one and immediately know what the right one will do, you have not caused anything at all. You have just read a label. It is the same as if I put a red marble in one envelope and a blue marble in another, mailed one to Tokyo, and opened the one on my desk. The moment I see red, I know Tokyo has blue. Nothing travelled. Nothing was spooky. I just found out something that had been true since the morning. That picture has a name in the literature. Physicists call them hidden variables, properties the particles genuinely have that the equations do not include. And underneath the technical language sits a claim about the world so plain that a child could state it. Everything that happens was already settled before it happened. The universe is not deciding, it is revealing. Sit with that for a second, because the whole of the next 2 hours grows out of it. If Einstein was right, then when that particle arrived at the detector and gave its answer, it could not have done otherwise. The answer was in its pocket the entire flight, and if that is true of particles, you have to ask how far up the ladder it goes, because you are made of particles, and so is your brain, and so was every thought you had this morning while you were deciding whether to get up. Now here is the part that makes this a genuinely great story rather than just an interesting disagreement. For 29 years, nobody could tell who was right, not because the question was too hard, because the two pictures made identical predictions. Every experiment anyone could design would come out the same way whether the particles carried their answers in advance or generated them on the spot. You could run the apparatus for 1,000 years and collect a mountain of data, and the mountain would be silent on the only question you cared about. The disagreement was real. It was profound. It was about the actual structure of reality. And it was, as far as anyone could see, permanently unobservable. Physics has a word for questions like that, and the word is not flattering. It is metaphysics. And when a question gets that label, what follows is a slow, polite exile. Erwin Schrödinger, reading the 1935 paper, was so taken with the phenomenon at its centre that he gave it the name we still use. He called it Verschränkung, which we translate as entanglement, and he wrote that it was not one of many interesting features of quantum mechanics, but the characteristic trait, the one that forces the entire departure from classical thinking. He saw immediately how big it was. It did not help. The question still could not be tested, and a question that cannot be tested does not get funding, does not get laboratory space, and does not get you tenure. There is a small human detail here that I find hard to let go of. Einstein was not entirely happy with his own paper. Podolsky had written the actual text, and afterwards Einstein complained in a letter to Schrödinger that the essential point had been buried under erudition. The most famous objection in the history of quantum mechanics, and its most famous author thought it had been badly written. That is a very ordinary sort of frustration to find at the root of something so large. So the situation, by the middle of the 20th century, was this. There existed a question about whether the world is the kind of place where things are decided in advance. The question was clearly stated. Two of the most brilliant people alive had taken opposite sides of it, and there was no experiment anywhere, even in principle, that could distinguish between the answers. The people who kept caring about it anyway were regarded gently as having wandered off. For almost 3 decades, that is where the matter sat. Not solved, not abandoned, just parked, in the corner of the discipline where the interesting but useless things go, gathering the particular kind of dust that settles on problems everyone has agreed to stop looking at. And then somebody looked at it again, on his own time, as a hobby, while being paid to do something else entirely. He found that the two pictures were not identical after all. He found that the difference between a universe where your answer is already in your pocket and a universe where it is not comes down to a number you can measure in a laboratory with equipment you can build. He also found something else, in the same few pages, that almost nobody talks about. And that second thing is what this entire video is really about. Part 2, the third assumption. John Stuart Bell had a day job, and it was not this. He was born in Belfast in 1928 into a family that could not easily afford to keep him in school, and he left at 16 to work as a technician in a university physics department before scraping his way into a degree. By the 1960s he was at CERN in Geneva, designing particle accelerators. That was the work he was paid for. He was very good at it. The other thing, the thing about entanglement and hidden variables and whether Einstein had been right, was something he did in the evenings and on leave, and he was quiet about it, because he understood perfectly well how it looked. In 1964 he took a year of unpaid leave and spent part of it in California. And in the middle of that year he wrote a short paper that took a question everyone agreed was untestable and made it testable. The trick is so clean that once you see it you cannot unsee it. So let me walk you through it slowly, because everything else tonight depends on you having this. Take your 2 entangled particles, one flying left, one flying right. At each end you have a detector, and each detector has a dial on it. The dial sets the angle you're measuring along. You can turn it wherever you like. Every time a particle arrives you get one of 2 answers. Call them yes and no, or up and down, or plus and minus. It does not matter what you call them. Now, if you set both dials to the same angle, both pictures of the world agree completely. The 2 particles always give matching answers, every single time, and that is not mysterious under either story. Einstein says they were printed with matching labels. Quantum mechanics says the first measurement fixes the second. Same data, no help. Bell's insight was to stop setting the dials to the same angle, turn one dial a little, not much, 30 degrees say. Now the answers do not match perfectly anymore. They match most of the time and disagree some of the time. Turn it further, they disagree more. Fine. Both pictures predict some falling off. Here is the question Bell asked. Is there a limit to how the disagreements can add up? And there is. If the particles are carrying pre-printed answers for every possible angle, if the answer really is in the pocket before the flight, then the way disagreements accumulate across different combinations of angles is constrained. There is a ceiling. You can do the arithmetic on the back of an envelope, and it works for any set of hidden variables you care to imagine, no matter how complicated, no matter how cleverly arranged. Pre-printed answers cannot disagree more than a certain amount in total, across the combinations. Quantum mechanics predicts a number above that ceiling. That is Bell's theorem. That is the whole thing. A universe where the answers were written in advance has a maximum. A universe running on quantum mechanics goes over it. And the difference between the deepest disagreement in 20th century physics and a Tuesday afternoon in a laboratory turned out to be nothing more than counting how often two lights blink together. I want to tell you where this was published, because it says something about how the field felt about the subject. Bell put it in a journal called Physics Physique Physica. It was brand new. It had a gimmick. It waived page charges, meaning it did not bill authors to print their work, which mattered to a man doing this on his own time. The journal folded after 4 years. For roughly the first decade, Bell's paper was cited a handful of times a year, mostly by people who already knew him. It is now one of the most cited papers in the history of the subject, and because of where he published it, John Bell never earned a penny from it. Now we come to the part I promised you, and it is the reason this video exists. Bell's proof needs certain things to be true in order to work. When people summarize it, in textbooks, in documentaries, in the article you skimmed once, they almost always list two. The first is locality. Nothing travels faster than light. What I do to my particle does not reach across and physically alter yours. The second is realism. And here I have to firewall something immediately because the popular version of this word has caused more confusion than any other term in modern physics. Realism, in Bell's technical sense, does not mean the world exists when you're not looking at it. It is not a claim about whether the moon is there when nobody checks. It means specifically that the measurement outcomes are determined by properties the particle carries, the pre-printed label, that is all. Anyone who tells you these experiments proved reality does not exist until observed has swapped a narrow technical term for a piece of poetry, and the swap is not innocent. Those are the two assumptions everybody lists. There is a third. For the proof to work, the angles you choose on those dials must be uncorrelated with whatever the particles are carrying. Your choice has to come from outside the system you are studying. If the dial settings and the hidden properties of the particles share a common source, if something, anywhere, at any time, arrange for them to line up, then the whole argument collapses, not weakens, collapses. The ceiling calculation assumes you could have turned that dial to any angle regardless of what was coming down the tube. Let me give you a concrete picture of what a failure of the third assumption would look like, because in the abstract it sounds like nothing at all. Suppose you are testing a new drug. You have 2 groups of patients, and you decide which patient goes into which group. The whole logic of the trial rests on the idea that your assignment is unrelated to how sick each person already is. Now suppose it turns out that some process you never knew about was quietly sorting the healthier patients into the treatment group every time. You did not cheat. You were not bribed. You made your choices in good faith and you believed they were yours. But the correlation was there, upstream of you, and every conclusion you drew from that trial is now worthless, not slightly weaker, worthless. The numbers you collected are real. They just do not mean what you thought they meant. That is what a failure of statistical independence does to a Bell test. And notice that from inside the experiment there is no way to detect it. Everything looks exactly the same. The data comes out clean. The apparatus behaves. You feel entirely free while you're turning the dial. Physicists call this statistical independence, or measurement independence, or, when they are speaking plainly rather than technically, the freedom of choice assumption. It is the third assumption. Hold on to that phrase, because we are going to come back to it several times tonight, and it is going to mean something different each time. There is a companion idea that goes with it, and it has an unlovely name, counterfactual definiteness. It is the assumption that it is meaningful to talk about what the result would have been if you had chosen the other angle. That sentence sounds harmless. It is doing enormous work. Every time you reason about an experiment you did not run, you are leaning on it, and like the third assumption, it is very difficult to check by doing experiments, because the only tool you have for checking things is the experiments. Here is what is strange about it. Go and look at how it is normally presented. In most treatments, it appears as a line of setup, a housekeeping condition mentioned once, waved through, never revisited. It is the physics equivalent of the small print, and you can understand why. The first two assumptions are grand statements about the structure of the universe. The third one sounds like a technicality about experimental procedure. It is not a technicality. It is a claim about you. Imagine being in the room where this is written down. It is 1964. The desk is not tidy. There is a man in his mid-30s working through an argument on paper, and he has to state, explicitly, the conditions under which his proof holds. He writes the first condition, about signals and light speed, and it is a statement about the fabric of space-time. He writes the second, about properties and outcomes, and it is a statement about matter. Then he writes the third, and the third is not about space-time or matter at all. The third is about whoever will one day be standing at the apparatus with a hand on the dial. It says, assume that person's choice came from somewhere else. Assume it was theirs. He writes it in the same handwriting at the same speed, with the same lack of ceremony as the other two, and moves on to the next line, because at that moment it is simply the least interesting of the three. He has no way of knowing that half a century later it will be the only one still standing, and Bell knew. That is the thing that stops me every time I come back to this. He was not careless about it, and he did not hide it. Over the following 2 decades he returned to that third condition in talks and in essays, turning it over, poking at it, saying out loud that it was the one that could not be enforced by any apparatus. The man who built the test spent the rest of his life being the person most willing to say what the test could not do. We will hear from him directly, in his own words, much later tonight, and I would ask you to remember at that point that he had been circling this since the beginning. The paper goes out. It disappears into an obscure journal that is about to fold, and somewhere, in a basement in California, a graduate student who has not started this yet is about to be told that building the machine is a waste of his career. Part 3. The Basement at Berkeley. The first person to take Bell's paper seriously enough to build something was a young man who was hoping to prove it wrong. John Clauser came across the paper in the late 1960s, at a point in his life when he was supposed to be doing radio astronomy. He read it, understood what it made possible, and went looking for someone who had already done the experiment. Nobody had. Nobody had even tried. 5 years had gone by since Bell published. The entire foundations of quantum mechanics were sitting there waiting for a verdict, and the machine that could deliver it had not been built because no serious physicist wanted their name on it. So Clauser wrote to Bell, and to a few others, and asked whether he was missing something. Bell wrote back and said, in effect, "No, you are not missing anything, and please go and do it." Before any of that could happen, though, there was a piece of theoretical plumbing to sort out. Bell's original inequality was written for an idealized experiment. Perfect detectors, no losses, everything clean. Real laboratories do not work like that. So in 1969, 4 physicists, Clauser himself, along with Michael Horn, Abner Shimoni and Richard Holt, published a reformulated version designed to survive contact with actual equipment. It is known ever after by their initials, and it is the version that essentially every experiment since has measured. That paper is the reason the test moved from a thought experiment to a shopping list. What happened next is one of my favourite sequences in 20th century science, partly because of how unglamorous it is. Clauser ended up at the University of California, Berkeley, and teamed up with a graduate student named Stuart Friedman. They were given very little money in a basement. They scrounged equipment. They were told, by people senior to them and in a position to affect their futures, that this was not a real problem and that working on it would mark them. Here is what they built. They took calcium atoms and heated them into a beam. Then they hit those atoms with light to kick their electrons into an excited state. As each atom relaxed back down, it did so in 2 steps, and each step released a photon, a cascade, 2 photons in quick succession, flying off in roughly opposite directions with their polarizations correlated. That correlation was the entanglement they needed. On each side of the beam they put a polarizing filter, then a photomultiplier tube to catch whatever got through, and then a counter that tallied how often both sides registered a hit at the same moment. Turn the filters to different angles, count the coincidences, compare against the ceiling. They ran it for around 200 hours of data collection, 200 hours of two lights blinking in a basement, to settle an argument that had been going for 37 years. The answer came back at roughly 6 standard deviations past the ceiling. In the language physicists use, 6 sigma means the odds of getting that result by accident, if the pre-printed answer picture were correct, are somewhere around 1 in 500 million. It was published in 1972 in Physical Review Letters, Volume 28, page 938. Einstein's picture, in its simplest form, had just failed its first laboratory test, and John Clauser was disappointed. I want to slow down here, because this is the human centre of the early part of the story. Clauser has said, more than once and in public, that he went into that basement expecting to prove Einstein right. He preferred the world where things are settled in advance. He thought it was the sensible world, the one a physicist should want, and he built the apparatus in the hope of demonstrating it. Instead, his own equipment handed him the opposite answer, and he trusted the equipment more than he trusted his preference, which is the entire job, and which is much harder than it sounds when the result is one you did not want. The professional cost was real. Clauser spent years afterwards in soft money positions, moving between temporary appointments, doing work that the field regarded as slightly eccentric. He did not get a comfortable chair somewhere for having answered one of the oldest questions in the subject. He got a reputation for being interested in the wrong things. And then there is Stuart Friedman, the graduate student who built it with him, whose thesis this was. Friedman went on to a long and respected career in nuclear physics. He died in 2012, at 68. 10 years later, in 2022, the Nobel Prize in Physics was awarded for exactly this line of work, for experiments with entangled photons and the violation of Bell inequalities. Clauser was one of the 3 names on it. The prize is not awarded posthumously. Friedman had been dead a decade. He built the first machine that tested whether the universe decides things in advance, in a basement, on almost no money, while being told it was a waste of his time, and he did not live to see anybody hand him anything for it. And there is a wrinkle here that almost never gets told, which I think is one of the most instructive things in the whole story. At roughly the same time, another group at Harvard, Richard Holt, one of the authors of that reformulated inequality, working with Francis Pipkin, ran their own version of the experiment. They got the opposite answer. Their data sat comfortably inside the ceiling, which is to say it supported Einstein. 2 experiments, aimed at the same question, returning contradictory verdicts. This is what science actually looks like from the inside, and it is nothing like the tidy version. It took years to work out what had gone wrong, and the answer was almost absurdly mundane. Stress in the glass of the bulb containing their atoms was subtly rotating the polarization of the light passing through it. A mechanical strain in a piece of glassware had produced a false answer about the fundamental structure of reality. Holt and Pipkin never formally published the result. They knew something was off, and they said so, and they waited. I find that reassuring rather than unsettling. The reason we believe the Bell test today is not that the first one came out a particular way. It is that people spent 50 years trying to break them. Now, having said all that, I have to tell you the other half, which is that the 1972 experiment was full of holes, and everybody knew it, including the people who built it. The polarizer angles were set by hand. Somebody walked over, turned a knob, walked away, and left it there for hours while the counts accumulated. That means the setting was fixed long before most of the photons in that run were even created, which, if you are worried about the settings being correlated with the particles, is about the worst arrangement you could design. The detection efficiency was terrible. Photomultipliers of that era caught a small fraction of the photons that actually arrived. So the conclusion required an extra step of reasoning. Assume the ones you caught are a fair sample of the ones you missed. That is a reasonable assumption. It is also precisely an assumption. And the 2 arms of the experiment sat a few meters apart on the same optical bench, in the same basement, which means light had plenty of time to carry news from one side to the other before either measurement was finished. If you wanted to insist that some ordinary signal was coordinating the 2 detectors, nothing in that apparatus stopped you. None of this was hidden. It was in the paper, and each of those holes was about to be given a name, written down on a list and handed to the next generation as homework. Part 4. Changing the question. While the answer is already in flight. The obvious complaint about the Berkeley experiment was the one about distance, and it is worth stating the complaint properly, because the fix for it is one of the most elegant things anyone has ever done with a bucket of water. If your two detectors sit a few meters apart and the settings have been fixed for hours, then there is nothing in the physics stopping information from getting around. A signal moving at the speed of light crosses a few meters in a few billionths of a second, which is an eternity compared with how long the measurement takes. So a critic could say, fine, your particles are correlated, but perhaps the left detector is somehow influencing the right one through some ordinary mechanism we have not identified. The experiment does not rule that out. It cannot. Everything is too close together, and everything has been sitting still for too long. I should pause and firewall something here, because at this point in the story, a lot of people reach a conclusion that is not true. Nothing in any of this lets you send a message faster than light. Not one experiment in the whole 70-year chain has ever transmitted a single bit of usable information faster than a photon could carry it. The correlations between the two sides are perfect and instantaneous, but each side on its own sees nothing but random noise. You only discover the correlation afterwards by comparing the two lists, and to compare the list you have to phone the other laboratory at the speed of light, like everybody else. Relativity is not bruised by any of this. It walks away entirely intact, which is one of the stranger facts about the whole business. To rule it out, you would need to change the setting on one side so late and so fast that no signal moving at light speed could carry the news to the other side before the other measurement was finished. That sounds impossible. In the early 1980s, a French physicist called Alain Aspect did it. Aspect was working at the Institut d'Optique at Orsay, just outside Paris. He had chosen this as his doctoral project, which was, again, the sort of decision that senior people warned you about. He's said to have gone to see Bell to discuss it, and Bell's first question was whether he had a permanent position, because without one this work would end him. Aspect did have one. He proceeded. He built 3 experiments between 1981 and 1982, each better than the last. The third one is the famous one. The first 2 experiments in the series are worth a sentence each, because they show the method. The first, in 1981, simply improved the signal enormously. Aspect used a laser-driven calcium source that produced entangled pairs at a far higher rate than Berkeley had managed, turning 200 hours of counting into minutes. The second, in 1982, replaced the simple polarizers with 2-channel analyzers, so that instead of a photon either passing or vanishing, every photon was sorted into one output or the other. That mattered because it removed a whole layer of assumption about the ones that went missing. Only then did he go after the timing. Here is the device at the heart of it. In each arm of the apparatus, Aspect installed an acousto-optic switch. Inside it, a transducer drove ultrasonic standing waves through water at around 25 MHz. Those sound waves compressed the water in a regular pattern, and a regular pattern of compression in a transparent medium acts like a diffraction grating. It bends light. By driving the sound at the right frequency, Aspect could flip a photon between 2 different paths, leading to 2 different polarizer settings, roughly every 10 nanoseconds. 10 nanoseconds is 10 billionths of a second. The 2 arms of his experiment were about 12 meters apart. Light takes around 40 nanoseconds to travel 12 meters, so the setting on the left side was changing 4 times faster than any signal could possibly cross the gap. Let me put you in that room, because I think the physicality of it matters. It is 1982, in a laboratory outside Paris, and the room is humming. Not metaphorically. There is an actual acoustic tone in the air, because there is sound being driven through water at 25,000 cycles a second in 2 separate boxes on either side of the bench. Between them sits a source of calcium atoms, throwing out pairs of photons in opposite directions. One of those photons leaves the source and starts its 12-meter journey. It is moving at 300,000 kilometers a second, so the journey takes it about 40 billionths of a second, and in that time nothing about it changes. It has no properties in reserve for this, and while it is in flight, in the box waiting for it, the water is being squeezed and released, and the question it is about to be asked flips over. Once, twice, 3 times, 4, before it arrives. The photon reaches the switch. The water happens to be in one particular state at that instant. The photon goes left rather than right, into one polarizer rather than the other, and is asked a question that did not exist as a decision when it set out. On the far side of the bench, 12 meters away, its partner is asked its own question, and no news of either question can reach the other end in time. The counters click, and they click together far more often than a universe of pre-printed answers is allowed to allow. The violation held. Aspect's numbers came in comfortably past the ceiling, and this time you could not explain them away with a signal, because there was no time for a signal. Now, in the spirit of honesty that runs through this entire story, I have to tell you what was still wrong with it. The switching was periodic. The water was oscillating in a regular rhythm, which means the sequence of settings was not truly random. It was predictable, if you knew the frequency and the phase. Critics pointed this out at the time, and they were right to. A pattern that repeats is a pattern that something could, in principle, have anticipated. Aspect knew this perfectly well. He was closing one hole, not all of them, and he said so. The people who fixed that were in Innsbruck 16 years later. In 1998, a team including Gregor Weiss and Anton Zeilinger ran the experiment across 400 meters of the university campus, using optical fiber to carry the photons, and, this is the key part, they drove the setting choices with genuine physical randomness rather than a repeating rhythm. Each side had its own independent random generator, running fast enough that the choice on one side was made after any signal from the other side could have arrived. Not a rhythm, not a pattern, a fresh coin flip every time at both ends, too late for either end to know about the other. That experiment closed the locality loophole properly, and it is the one that turned Aspect's demonstration into an airtight result about distance. 400 meters does not sound like much next to the numbers we're going to reach later tonight. But it was the first time the geometry was genuinely on the experimenter's side. But the principle had been established, and it was a big principle. You could change the question while the answer was already on its way, and the universe still refused to behave the way Einstein wanted it to. There is a detail in the Innsbruck setup I've always liked. The two stations were far enough apart and the timing tight enough that the experimenters had to account for the finite speed of the electronics themselves. The wires carrying the signal from the random generator to the switch had a length, and that length had to fit inside the budget. When your experiment is testing whether the universe permits influence at a distance, you end up measuring your own cabling as though it were a suspect. That is the level of care that 50 years of criticism produces. 40 years later, in 2022, the Nobel Prize in Physics went to Alan Aspect, John Clauser and Anton Zeilinger for this line of work. The citation is carefully worded. It credits the experiments and the violation of Bell inequalities and the founding of quantum information science. It does not tell you what the results mean, because the committee, sensibly, was not going to touch that. John Bell was not on the list. He died in 1990 of a brain hemorrhage at 62, 32 years before the prize was given for testing his theorem. He had been nominated that same year. The prize is not awarded to the dead. So the list of ways to be wrong was getting shorter. Distance, addressed, at least in principle. What remained was everything else, and somebody was about to sit down and write the whole catalogue out. Part 5. A Catalogue of Ways to be Wrong. Somewhere in the 1980s, the physicists working on this did something that I think is genuinely admirable, and that almost no other field does with the same discipline. They sat down and wrote out a list of ways they might be wrong, not a vague acknowledgement that science is provisional, an actual enumerated catalogue of specific mechanisms by which their own celebrated results could turn out to be an artifact. Each one named, each one written into the literature, each one treated as a piece of unfinished business that somebody would eventually have to go and close. They called them loopholes, and then, over the following 30 years, they went and closed them, roughly one per decade, at enormous cost and considerable personal effort. Keep this phrase in your head because we will come back to it. A list of ways to be wrong. It is the best thing science does. It is the thing that separates a result you should believe from a result somebody merely announced. Before I read it out, it is worth knowing what the actual measured quantity looks like, because it is less mysterious than you would think. The experiments combine 4 different combinations of dial settings, 2 choices on the left, 2 on the right, into a single number. Physicists call it S. If the particles carry pre-printed answers, S cannot exceed 2. That is the ceiling. Quantum mechanics allows S to reach 2 times the square root of 2, which is about 2.828. Real experiments, dragged down by imperfect optics and lossy fibers, typically land somewhere between 2.4 and 2.7. So the entire empirical difference between a universe that decides in advance and a universe that does not lives in a margin of about 40% on one number. Every loophole on the list below is a story about how that margin might be fake. Here is the list. The first is the detection loophole, sometimes called the fair sampling loophole. Your detectors do not catch everything. In the early experiments, they caught a tiny fraction. So when you tally up your correlations, you are tallying the ones you happen to see, and then assuming that the ones you missed would have behaved the same way. If you're willing to imagine a hidden variable model that is clever about which particles get detected, one where the particles that would have spoiled the pattern quietly fail to register, then you can reproduce the quantum predictions with no strangeness at all. To close this one, you need your detection efficiency above a threshold, and for the version of the inequality used in modern photon experiments, that threshold sits at around 66%. That does not sound demanding until you learn that for decades nobody could build a single photon detector anywhere near it. The second is the locality loophole, which we have just spent a part on. If the two measurement events are not separated in the specific way relativity cares about, if a light-speed signal has time to get from one to the other before the second is complete, then you have not enforced no communication, you have merely assumed it. Aspect made it hard. Innsbruck made it airtight. The third is the coincidence time loophole. This one is subtle and it surprised people. In a photon experiment, you have to decide which detection on the left counts as the partner of which detection on the right, and you do it with a timing window. Anything within a few nanoseconds counts as a pair. It turns out that if the hidden variables are allowed to shift the arrival time slightly, then your choice of window can manufacture an apparent violation out of a perfectly local model. The pairing procedure itself becomes part of the physics. The fourth is the memory loophole. If the apparatus retains something from previous runs, if trial number 4000 is not statistically independent of trial number 3999, then the standard statistical analysis, which assumes each trial is a fresh independent sample, overstates your confidence. Modern analyses fix this by using methods that make no independence assumption between trials at all. It is worth sitting with why there were so many. When people outside science hear that a famous result had 5 known ways of being wrong, the instinct is to conclude that the result was shaky. The opposite is true. A field that can name 5 specific failure modes for its own flagship experiment is a field that has thought about that experiment much harder than most. The loopholes exist in the literature because somebody went looking for them on purpose, usually somebody who believed the result and wanted it to survive scrutiny. Nobody was forced to publish these. There was no external auditor. They audited themselves, in public, for decades, and then spent careers fixing what they found. Those 4 are engineering problems. I want to be precise about what I mean by that. They are hard engineering problems. Some of them took 30 years, and inventions that did not exist when the loophole was named. But they are the kind of problem where you can see the shape of the solution from where you are standing. Better detectors, longer distances, tighter timing, smarter statistics. Each one is a thing you can build your way out of, and each one, eventually somebody did. Take that detection threshold as an example of the timescale involved. When the detection loophole was first described, the best available single photon detectors caught something in the region of 10 or 20% of what arrived. The number you needed was 66. That gap was not a matter of trying harder with the equipment on the bench. It required a detector technology that had not been invented. The devices that eventually did it, superconducting nanowires, strips of metal cooled to within a couple of degrees of absolute zero, where a single arriving photon deposits just enough energy to break the superconductivity and register as a voltage spike, were not available in any laboratory until the 2000s. The loophole sat open for 30 years, not because nobody cared, but because the thing required to close it did not yet exist in the world. And then there is the fifth. The fifth is the freedom of choice loophole, and it is the third assumption wearing a laboratory coat. It says, what if the process that chooses your measurement settings is itself correlated with the properties of the particles you are measuring? Not through a signal, not through any influence travelling from one to the other, simply because both of them came out of the same past, and something in that shared past lined them up. If that is the case, then everything above is irrelevant. You can have detectors that catch every single photon. You can put your 2 stations on opposite sides of the planet. You can time everything to the picosecond. None of it matters, because the argument never depended on those things alone. It depended on your dial settings being unrelated to what was coming down the tube, and that relationship is not something any amount of apparatus can enforce. The fifth item is not an engineering problem. I am not going to explain yet why it is not, because the reason only lands properly once you have watched people try. And they did try. What follows is 30 years of some of the most ingenious experimental physics ever performed, aimed squarely at that fifth line on the list, by people who understood exactly what they were up against. 4 of the 5 items were about to be crossed off. The 5th one is still on the list tonight. It will be on the list tomorrow, and by the end of this video you're going to understand something uncomfortable about why. Part 6. The Year the Walls Came Down. 51 years after Bell wrote his paper, 3 separate teams closed the first 2 items on the list within 4 months of each other. Nobody planned that. There was no coordination. It happened because the technology finally arrived and several groups had been waiting at the starting line for it, and when it arrived they all went at once. 2015 is the year the phrase loophole-free Bell test entered the literature, and it is one of the more satisfying years in modern experimental physics. The first one out was in the Netherlands, and it took the least obvious route. Ronald Hansen's group at Delft University of Technology published in Nature in October 2015, and instead of using photons for the whole experiment, they used diamonds. Specifically, they used a defect called a nitrogen vacancy center. Take a diamond, which is a lattice of carbon atoms in a very orderly arrangement. Now go into that lattice and swap one carbon atom for a nitrogen atom, and remove the carbon atom sitting next to it, leaving a gap. That pairing, a nitrogen atom beside an empty space, behaves like a single artificial atom trapped inside the crystal. It has an electron whose spin you can prepare, manipulate and read out. And because it is locked inside a diamond, it stays put, and it stays coherent for a usefully long time even at room temperature. This is the same physical system people are now trying to use to sense magnetic fields inside living tissue, so it has commercial descendants. But in 2015 its job was to settle an argument from 1935. Hansen's team put 2 of these diamonds in separate laboratories at opposite ends of the Delft campus, 1,280 meters apart. To give you a sense of that distance in the units that matter here, light takes about 4.27 microseconds to cross it. In a laboratory where events are usually timed in nanoseconds, 4 microseconds is not a tight window. It is a canyon. Everything they needed to do at each end could be finished long before any signal from the other end could possibly arrive. Now, the clever part. They did not send an entangled pair from the middle out to the 2 ends. That is the obvious design, and it has a fatal flaw. Photons get lost in fibre, and every lost photon reopens the detection loophole. Instead, each diamond emitted a photon that was entangled with its own local electron spin. Both photons then travelled to a third station sitting between the 2 laboratories, where they were brought together and interfered. And here is the trick. When those 2 photons interfere in one specific way, and the detectors at the middle station register one specific pattern, that event does something remarkable. It leaves the 2 electron spins, still sitting in their diamonds more than a kilometre apart, entangled with each other. The photons are consumed. The entanglement transfers to the 2 things that never met. This is called entanglement swapping, and its enormous advantage is that it announces itself. That middle station click is a herald. When you see it, you know, before you have measured anything at either end, that you now have a genuine entangled pair ready to be interrogated. You're no longer selecting your data after the fact and hoping the sample was fair. The pair was declared before the question was asked. The detection loophole does not just get closed, it stops being applicable. There is a lovely footnote to this. The idea of a heralded, announced in advance entangled pair was not new in 2015. Bell himself had floated something very like it, decades earlier, when writing about what an ideal version of his experiment would look like. He talked about event-ready detectors, an arrangement where you know you have your pair before you interrogate it, precisely so that nobody can accuse you of choosing your data afterwards. He described the fix long before anyone could build it. The Delft experiment is, in a real sense, the machine Bell sketched in an essay, constructed by people who were children when he wrote it. The price for this is brutal, and it is worth understanding because it is the reason this took until 2015. That heralding event is spectacularly rare. Most attempts produce nothing. The 2 photons have to survive the journey down the fibre, arrive at the middle station within a very narrow timing window, be indistinguishable from one another in every respect, and interfere in exactly the right way. The vast majority of the time, one of those conditions fails and the attempt is discarded. The Delft team ran for about 220 hours of measurement, spread across 18 days. They collected 245 usable trials. 245, that is the entire dataset. Compare that with a particle physics experiment, where a collider produces hundreds of millions of collisions per second, and you get a feeling for how thin the ice was. With 245 trials, the statistics come out to a p-value of 0.039, which means that if the pre-printed answer picture were true, you would expect to see data this extreme about 4% of the time by chance alone. That is above the conventional threshold for significance, which is to say it counts. But it is nowhere near the crushing numbers physicists prefer, and the team said so, plainly, in their own paper. They had done something nobody had done in 51 years, and they described their own result as a violation that was statistically significant, without dressing it up. Think about what that means as a working experience, because I find this the most human part of the 2015 story. You're in a laboratory. You have built one of the most sophisticated pieces of apparatus on the planet. It runs continuously, and on a good day, it produces perhaps a dozen events that count. Everything else, thousands upon thousands of attempts, is thrown away because a photon scattered in a fibre or arrived 4 nanoseconds late. You sit with that for 18 days, watching a counter that barely moves, knowing that the entire weight of the result rests on whether the number gets high enough before something in the setup drifts out of alignment. That is what closing a 51-year-old question actually looked like. It looked like waiting. I like them enormously for that. 2 months later, the numbers arrived. In December 2015, 2 groups published back-to-back in physical review letters. One was at the National Institute of Standards and Technology in Boulder, Colorado, led by Lyndon Schaum. The other was in Vienna, at the Institute for Quantum Optics and Quantum Information, led by Marissa Justina and including Anton Zeilinger. Both went back to photons, and both could now do it, because the superconducting nanowire detectors we talked about earlier had finally become good enough. Detection efficiencies above 90%, well past the threshold. The loophole that had stood since the 1970s simply evaporated in the face of better hardware. Both experiments also had their stations far enough apart, and their random settings generated late enough to enforce the locality condition at the same time. The Vienna result came out with a p-value of about 3.7 times 10 to the minus 31. I should contextualize that number, because a string of zeros stops meaning anything after about the 4th one. A p-value of 3.7 times 10 to the minus 31 means that if the universe really did run on pre-printed answers, and you performed this experiment once every second, you would expect to see a fluke this extreme roughly once in a span of time, about 10 billion times longer than the current age of the universe. It is not the kind of number you argue with. Physicists conventionally announce a discovery at 5 standard deviations. This was far past that, and there is something worth noticing in how the 2 results sit together. The Delft experiment had the elegant design and thin statistics. The Boulder and Vienna experiments had overwhelming statistics and a more conventional design. Neither on its own would have settled matters as firmly as the 3 of them arriving within a season of each other by different routes, using different physical systems, diamonds in one case, photon pairs from nonlinear crystals in the others, and landing on the same answer. That is what convergence looks like, and it is worth more than any single number in any single paper. So by the end of 2015, the situation was this. Detection loophole, closed. Nanowires did it. Locality loophole, closed. Distance and fast random switching did it. Coincidence time and memory loopholes, handled with careful analysis methods that make no assumption of independent trials. 4 items crossed off a list that had taken half a century to work through. Einstein's picture, in the specific form he proposed it, was finished. Not doubted. Finished. You cannot have a world that is both local and carrying pre-printed answers, and the experiments that establish it are now airtight in every direction anyone had been able to specify. It is also worth saying what did not happen in 2015, because the popular telling gets this backwards too. Quantum mechanics was not confirmed by these experiments in any sense that was in doubt. Nobody expected the equations to fail. They have not failed a prediction in a century. What was settled was something narrower and more interesting. Not whether quantum mechanics works, but whether any theory of a particular shape, local, with definite pre-existing outcomes, could work instead. The answer is no. The equations were never the thing on trial. The picture underneath them was, every popular account of this story ends here. This is the triumphant part. This is where the documentary music swells and somebody says that the universe is stranger than we imagined. But go and read those 3 papers, the actual papers, the Delft one and the Boulder one and the Vienna one, and look at what the authors themselves wrote about their own results. In every case, somewhere in the discussion, there is a paragraph acknowledging the item that is still on the list. They do not bury it. They name it. The Vienna paper discusses it explicitly. The Delft paper discusses it explicitly. They had just closed the 2 loopholes the whole field had been fighting for 51 years, and they used part of their moment to point at the one they had not touched. Because none of these experiments, not one of them, not with any conceivable improvement in detectors or distance, had done anything at all about the 5th item. The settings in all 3 experiments were chosen by random number generators, very good ones, quantum random number generators in some cases, laser phase noise in others, devices whose output is as unpredictable as anything humans know how to build. And a random number generator is a physical object. It sits in a room, it is made of atoms, it has a past, it came from somewhere. If the worry you're trying to eliminate is that the settings might be correlated with the particles, because both emerge from the same shared history, then a box on a bench in the same building as the particle source is not obviously outside the problem. It is, arguably, right in the middle of it. The 5th item needed something else. It needed a source of decisions that could not plausibly have been arranged in advance by anything in the vicinity. And in 2016, somebody had an idea about where to find one. Part 7. If you are free, so is the electron. Before we go chasing the 5th item across the universe, we need to stop and understand exactly what is at stake if it turns out to matter. And for that we have to talk about 2 mathematicians at Princeton who gave a theorem a name so provocative that people have been misquoting it ever since. In 2006, John Conway and Simon Koshin published a paper in Foundations of Physics. They called it the free will theorem. 3 years later, they published a strengthened version in the Notices of the American Mathematical Society, and called that one the strong free will theorem, which tells you they were not backing away from the branding. Conway was, by any measure, one of the most inventive mathematicians of his generation. He's probably best known outside mathematics for inventing the game of life, that grid of black and white squares where a handful of simple rules produce endlessly complicated behaviour. He was also, by every account, a serious troublemaker in the best sense. A man who liked an argument and had no interest in a result that nobody noticed. He said as much about the name. He chose it because he wanted the theorem argued about rather than politely filed. It worked. It also guaranteed that most people who encounter it get it exactly backwards, so let us do this carefully. The theorem is a conditional. That is the entire point of it, and it is the part that gets dropped in every popular retelling. It does not say free will exists. It does not say free will does not exist. It says, if this, then that. Here is the if. Suppose that when an experimenter chooses which axis to measure a particle along, that choice is not a function of the entire prior history of the universe. In other words, suppose the choice is not already fully determined by everything that has ever happened. That is what Conway and Koshin mean by free, a narrow, technical, entirely unmystical sense of the word. No consciousness required, no soul required, just, not fixed in advance by the past. Here is the then. If that is true of the experimenter, then it is also true of the particle. The particle's response to the measurement is not a function of the entire prior history of the universe either. The answer it gives is not written down anywhere in advance. Not in the particle, not in the apparatus, not in the state of the universe 1 billion years ago. That is the theorem. If you are free, in that specific sense, so is the electron. Now, Conway and Koshin were asked about 1,000 times whether they were claiming electrons are conscious, or that particles make decisions, or that there is some sort of proto-mind in matter. They said no, repeatedly, in print and in lectures, and they were visibly irritated about having to. The theorem says nothing whatsoever about awareness, intention, deliberation, experience, or anything that feels like anything from the inside. It is not a claim about mind, it is a claim about determination. The only property being discussed is whether something is fixed by the past. It is worth pausing on the word free here for a moment longer, because the theorem's use of it is much thinner than the everyday one, and the gap between them is where most of the confusion lives. When you and I talk about free will over a drink, we usually mean something rich, that we deliberated, that we weighed things, that the decision expressed who we are, that we could have gone the other way and it would still have been us going the other way. Conway and Koshan are not interested in any of that. Their definition strips it down to a single question with no adjectives in it. Is this event a function of what came before? Yes or no? A coin flip passes their test. A radioactive decay passes their test. Neither of those has a personality. The theorem is not about agency in the sense you care about at 3 a.m. It is about whether the future is fixed. That thinness is a feature, not a bug. It is what lets the result be a theorem rather than an opinion. But it does mean you should be careful about what you carry away from it. The machinery underneath it comes from an earlier result that Koshan had co-authored back in 1967 with Ernst Specker, and which is one of those theorems that deserves to be far better known than it is. The Koshan-Specker theorem shows that you cannot assign definite pre-existing values to all the measurable properties of a quantum system in a way that is consistent and independent of what else you choose to measure alongside it. Not merely that we do not know the values, that there is no consistent way to assign them at all. Conway and Koshan took that, combined it with the Bell-style correlations, added the freedom assumption about the experimenter, and out came the conditional. So far this is interesting. Here is the part that keeps people awake. Every conditional has a contrapositive, and the contrapositive is logically identical to the original. If A implies B, then not B implies not A. Always. There is no wriggling out of it. So, if the electron's response is a function of the prior history of the universe, if it was determined all along, then the experimenter's choice was determined too. Read that again, slowly, because it is doing something rather cruel. The theorem does not tell you which branch is true. It offers no evidence for either. What it tells you is that you cannot pick and choose. You cannot have the comfortable arrangement where the universe is a determined machine at the level of particles, obeying strict laws with everything settled since the beginning, and also a place where you are meaningfully free to have chosen otherwise this morning. Those two things are not independent claims that can both be held. They are welded together, mathematically welded, not poetically, and the welding runs both directions, which is the part I find genuinely disorienting. Most people, if pressed, will say something like, obviously the electron is determined, that is what physics is, and my own freedom is a separate question about brains and complexity and levels of description. The theorem says no. Those are the same question. Whichever answer you give for one, you have given for the other. There is a common objection at this point that deserves an answer, because it is the first thing a thoughtful person says. Surely, you might think, quantum randomness gives us an out. If the electron's answer is genuinely undetermined, if it really is a fresh throw of the dice each time, then the universe is not a fixed machine, and there is room for me in it. Hold that thought. We're going to come back to it in a while, and when we do it, is going to turn out to be one of the most comfortable-looking exits in this entire subject, and one of the least load-bearing. Randomness solves a smaller problem than people expect it to. I want to name a misreading here, because it is everywhere and it is worth immunizing yourself against it. You will find articles claiming the free will theorem proves that human beings have free will. It does not. It cannot. It is a conditional, and its premise is exactly the thing at issue. If you assume the experimenter is free, you get a conclusion about particles. If you deny the premise, the theorem is silent about you and simply does not apply. Conway and Koshan said this themselves, repeatedly in the papers. The theorem takes free will as an input, and tells you what else you have to accept if you keep it. It does not hand it to you. Conway died in April 2020 of complications from a virus that was at that point a few months old, and the obituaries mostly led with the game of life, the grid, the gliders, the little self-replicating patterns that a generation of programmers built as their first real project. There is something fitting about that, though I doubt he would have put it this way. He spent part of his career showing that a universe of simple deterministic rules can generate behavior nobody could have predicted from the rules, and another part of it proving that if you are not determined, neither is the smallest thing in the world. There were objections, of course, and serious ones. Several philosophers and physicists argued that the theorem's freedom premise is stronger than Conway and Koshan admitted, or that deterministic interpretations of quantum mechanics slip out of it by denying the premise from the start. which is true and which Conway and Cochin cheerfully agreed with, because that is exactly what a conditional is for. The most substantial pushback came from people working on objective collapse models, who argued that a genuinely random collapse process satisfies the theorem's conclusion without anything interesting following from it. That argument ran in the journals for several years and has not fully settled. None of it touches the structure of the result. It touches how much you should care about the result, which is a different and more interesting fight. So hold both halves in your head as we go forward. Half 1, the entire experimental campaign we have been following, Berkeley, Orsay, Innsbruck, Delft, Boulder, Vienna, assumes the experimenter's choice comes from outside the system. That is the third assumption. That is the fifth item on the list. Half 2, if that assumption is false, then by Conway and Cochin, the particles are determined too, which means the pre-printed answers Einstein wanted are back on the table, Bell's theorem does not apply, and the entire 70-year result about the strangeness of the world quietly dissolves. The two halves are the same hinge. Everything swings on it, which is why, in 2016, physicists went looking for a source of choices that nothing in the universe could plausibly have arranged in advance. And the first place they looked was not the sky. It was us. Part 8. 100,000 people on a Wednesday. Let us step back for a moment and put the pieces on the table where we can see them all at once, because we are about to make a turn, and I want you carrying the right things into it. In 1935, Einstein said, "The world must have its answers written down in advance." In 1964, Bell showed that this claim makes a measurable difference, but only if three things are true, and the third of them is that whoever turns the dial could have turned it elsewhere. From 1972 to 2015, physicists built a chain of increasingly extraordinary machines and crossed 4 items off a list of ways they might be wrong. Better detectors, greater distances, faster switching, sharper statistics. All of it worked, and Einstein's picture, in the shape he proposed it, is finished. And the 5th item, the one about whoever is holding the dial, is exactly where it was in 1964, untouched. Not because anyone forgot, but because every setting chooser anyone had used was a machine sitting in the same building as the experiment, made of the same kind of matter, with a past that reaches back into the same history. So the question became, where do you get a decision from? And in 2016, a consortium of laboratories tried the one thing nobody had tried, which was to ask people. On the 30th of November 2016, more than 100,000 human beings, in over 100 countries, logged into a website and were invited to do something faintly ridiculous. They were asked to type zeros and ones, as unpredictably as they possibly could. The project called them Bellsters, which I love, and it built the whole thing as a game. You would tap out a string of digits, and an algorithm would watch you, looking for patterns. If it could predict your next digit better than chance, it told you so and scored you down. If it could not, you scored well. The game was, in a very literal sense, a machine designed to punish you for being predictable and reward you for being free. That design was necessary because human beings are famously terrible at randomness. Ask someone to produce a random string, and they will systematically avoid repeats. Nobody wants to type 1, 1, 1, 1, because it does not look random even though a truly random string produces runs like that constantly. We underproduce clumps and overproduce alternation. We are, without knowing it, deeply patterned. The game existed to fight the participants' own instincts. The organizing institution was a photonics institute near Barcelona, and the coordination problem was genuinely difficult in ways that have nothing to do with physics. 12 laboratories in different time zones, all needing a live feed of unpredictable digits, all with different consumption rates, all running on a single day that could not be rescheduled. Spain supplied the largest single contingent of participants, which is unsurprising given where the project was based, but the map of contributions is scattered across every inhabited continent. It is one of the few genuinely global experiments in the history of the subject, and it ran on volunteers. Over that single day, those people produced 97,347,490 binary digits. Those bits did not sit in a database. They were routed, live, in real time, to 12 laboratories on 5 continents, where 13 separate experiments used them to choose measurement settings. On photons, on single-trapped atoms, on atomic ensembles, on superconducting circuits. The consumption rate was so high that at times the platform struggled to supply the labs faster than they could burn through the digits. There were moments on the 30th of November when the rate-limiting factor in a fundamental physics experiment was how fast people were willing to tap their phones. It is worth knowing what those 13 experiments actually were, because the variety is part of the point. Some were photon experiments of the familiar kind, entangled pairs sent to separate stations. One used single atoms held in optical traps. One used large ensembles of atoms, where the entanglement is spread across many particles at once, rather than living in a neat pair. One used superconducting circuits, the same technology that quantum computers are built from, cooled to a few thousandths of a degree above absolute zero. These are wildly different physical systems, obeying the same equations but built out of entirely different stuff, sitting in different countries under different roofs. They all got fed the same stream of human digits, and they all returned the same verdict. If you were looking for a way to argue that the result is an artifact of one particular kind of apparatus, that day removed it. Sit with the picture for a second. It is evening somewhere. Somebody is on a sofa with the television on in the background, phone in hand, thumb moving on the glass. 0, 0, 1, 0, 1, 1. They are concentrating a little, the way you do with a small game, trying to catch themselves before they fall into a rhythm, deliberately breaking the pattern when they notice one forming. It is the most ordinary thing in the world. A person on a couch, half watching something, tapping a screen. And 4,000 kilometers away, in a room they will never see, in a building they could not name, a photon is travelling down a length of optical fibre toward a crystal. That crystal has an orientation, and its orientation was set a few thousandths of a second ago by the last digit that person's thumb produced. The photon arrives. It is asked a question that a stranger on a sofa chose for it, without knowing they were choosing anything, and it answers. Somewhere else on the planet its partner is being asked a different question, chosen by a different stranger, and the two answers agree more often than a universe of pre-printed labels is allowed to permit. The results were published in Nature in May 2018, under a title that says exactly what it is: Challenging Local Realism with Human Choices. Local realism lost again, in 13 experiments at once. I should be careful and say what this did and did not accomplish in technical terms, because it is easy to oversell. The Big Bell test did not close the freedom of choice loophole. Nothing closes the freedom of choice loophole. We will get to why shortly. What it did was replace one kind of assumption with another kind of assumption. Instead of assuming that a laser's phase noise is uncorrelated with a photon's hidden properties, you assume that 100,000 human nervous systems, scattered across the planet, making choices in a game designed to defeat their own habits, are uncorrelated with a photon's hidden properties. Is that better? Most physicists think so, and I think so too. But it is a change of assumption, not an elimination of one, and the paper is scrupulous about saying so. Now here is the thing I keep turning over about that day. 100,000 people spread across more than 100 countries, most of whom had no real idea what the data was for, sat down and tried as hard as they could to be unpredictable. That is a very strange thing to ask of a species. It is a stranger thing for a species to volunteer for in those numbers, and the reason they were asked is this. Physicists needed a source of decisions that the universe could not have quietly arranged in advance. They looked at their random number generators, beautiful machines, the best available, and concluded that a box in the corner of the lab was not clearly outside the problem. So they went looking for the least mechanical thing they could find, and the best candidate anyone could name, the closest thing to a decision that comes from outside the machinery, was a person choosing to be free. The experiment could not measure whether they succeeded. That is the part that stays with me. There was no test built into the platform that could tell whether those 100,000 people were genuinely originating their choices, or whether every tap was the inevitable consequence of 100 billion years of physics grinding forward. No such test exists. The experiment simply took their effort at face value, because there was nothing else to take. 100,000 human beings, on a Wednesday, doing their best to be free, and the apparatus recording the digits without any possible way of checking whether they were. There is an old joke among people who work on this that the freedom of choice loophole is the only loophole where the correct experimental control is a philosopher. It is funnier when you realize it is nearly true. Every other item on the list has a piece of hardware that fixes it. This one has a premise, and premises do not come with a part number. The paper is careful about this. It says that if human choices contain even a small amount of genuine freedom, the conclusion follows. If it is a beautiful piece of work, and it is, at bottom, a very large and very sincere assumption wearing 97 million digits as a coat. Which is why, even as the Belsters were tapping away, the same broad community of physicists was already working on a different approach. If you cannot verify that people are free, then stop relying on people. Find something that made its decision so long ago and so far away that no conspiracy could reasonably have reached it. They found something, and to get to it they had to point a telescope at an object that was already ancient when the Earth was a cloud of dust. Part 9. Light older than the Earth. The strategy that emerged is one of the most beautiful pieces of reasoning I know, and it starts by admitting defeat. You cannot eliminate the freedom of choice loophole. Everyone involved understood that by 2016. So instead of trying to eliminate it, you make the conspiracy required to exploit it progressively more absurd. The logic runs like this. Suppose you are worried that your dial settings are correlated with the particle's hidden properties. Where did that correlation come from? It cannot have come from nowhere. Something in the shared causal past of the setting chooser and the particle source must have arranged it. So, make the setting chooser as old as you can. Push the required arrangement backward in time. If your settings are chosen by a device built last year, the conspiracy only needs to have been arranged last year. If your settings are chosen by something that made its decision 1,000 years ago, the conspiracy needs a 1,000-year head start. Keep going. See how far back you can force it before the idea becomes ridiculous. And there is one source of ancient decisions available to anyone with a telescope: light. Every photon arriving from a distant object carries properties that were fixed at the moment it was emitted, and it has not changed since. Its wavelength was set then. Nothing has touched it in transit. So if you use the color of an arriving photon to set your measurement angle, if the photon landing on the red side of a dividing wavelength turns your crystal one way, and a photon on the blue side turns it the other, then the physical fact determining your setting was established when that light left its source, not in your laboratory, not last year, then. In 2017, a team including Anton Zeilinger in Vienna and David Kaiser and Andrew Friedman at MIT took this to a mountaintop. They went to the Roque de los Muchachos Observatory on the island of La Palma in the Canaries. It sits at around 2,400 meters on the rim of an enormous volcanic caldera, and it was built there for the reason all such places are built where they are. The sky above it is dark and the air above it is steady. They set up their entangled photon source between two telescopes and pointed each telescope at a different star. The stars they used were a few hundred light-years away, around 600 in the primary runs, which means that the color of each arriving photon, the property that determined which question the experiment would ask, had been fixed 6 centuries earlier, before the telescope existed, before the observatory existed, before the experimenter's great-great-great-grandparents existed. If something arranged for those settings to be correlated with photons produced in a crystal on La Palma in 2017, it did the arranging while Europe was in the middle of the 15th century. The inequality was violated. There is a small detail in the 2017 Starlight run that I have always liked. To use a star as your random number generator, you have to keep the telescope tracking it across the sky for the whole run, which means the setting generating apparatus is physically rotating on a mount all night, following a point of light through the atmosphere while a quantum optics experiment runs a few meters away on a bench that must not vibrate. Two entirely different traditions of engineering, 19th century astronomical tracking and 21st century quantum optics, bolted together on a mountain because that was the only way to get a decision with a 600-year-old provenance. The following year, they went considerably further. In August 2018, the same broad collaboration published a paper in Physical Review Letters with a title that tells you the whole story: Cosmic Bell Test using random measurement settings from high redshift quasars. A quasar is the core of a young galaxy with a supermassive black hole at its center, actively swallowing matter. The material spiraling in gets compressed and heated until it outshines every star in the galaxy around it, sometimes by a factor of thousands. They are the brightest sustained objects in the universe, which is why we can see them from distances that are otherwise impossible. The team picked 2. The light from one had been travelling toward Earth for approximately 7.8 billion years, the light from the other for approximately 12.2 billion years. Let me follow one of those photons the whole way, because I think it is the only way to feel the size of what they did. It leaves an accretion disk, a whirlpool of superheated gas falling into a black hole in a galaxy that no longer looks anything like it does in this picture. The universe at this moment is less than half its current age. There is no sun. The gas and dust that will one day collapse into our solar system is still spread thin, part of some larger cloud, unremarkable. There is no Earth, no moon, nothing that will become either. The photon starts moving outward at the only speed it knows. It crosses the space between galaxies, and the space itself is stretching as it goes, so the photon stretches with it, sliding gradually toward the red end of the spectrum, losing energy not because anything took it, but because the distance underneath it keeps growing. Billions of years pass. Around it, gas clouds collapse, stars ignite and die, generations of them, and in one unremarkable spiral arm a new star lights up with a disk of debris around it. Rock accretes. An ocean forms. Something in that ocean starts copying itself. The photon is still travelling. It arrives finally at a mountain on a small island on a specific night, and passes through a piece of glass shaped by people who evolved from that ocean about 11 minutes of cosmic time ago. Behind the glass is a filter and a detector. The photon's wavelength, set 12.2 billion years earlier, in a galaxy that has since become something else entirely, falls on one side of a dividing line rather than the other. A signal goes out. A crystal a few meters away turns to a particular angle, and a photon born 3 microseconds ago in that crystal is asked a question chosen by light older than the planet everyone is standing on. The practical difficulties here are worth a moment, because the idea is elegant and the execution was not. Quasars are bright for their distance, but they are still faint by the standards of an experiment that needs a decision every few microseconds. Only a small fraction of the photons arriving at the telescope were usable. The rest were background light from the sky, or from the atmosphere, or arrived at the wrong moment relative to the entangled pair being generated. The team had to build detection electronics that could distinguish a genuine quasar photon from a stray one in real time, decide which side of the wavelength boundary it fell on, and communicate that decision to the polarization analyzer before the entangled photon arrived. All of that had to happen faster than light could cross the gap between the two stations, or the locality condition would break and they would have traded one loophole for another. They also had to worry about something that sounds almost paranoid until you think about it. Any photon that was not actually from the quasar, a cosmic ray hit, a thermal event in the detector, scattered moonlight, would inject a setting choice with a recent origin into the stream, and a sufficiently determined critic could build their conspiracy in that gap. So the analysis has to account for the estimated fraction of non-quasar events and fold it into the final claim. The paper does this explicitly. The violation came in at 9.3 standard deviations. For scale on that number, particle physicists conventionally announce a discovery at 5 standard deviations. 9.3 is a result you do not argue with under ordinary circumstances. It is also worth appreciating what a strange piece of instrumentation this makes. In every other experiment in this story, the random number generator is a component, a box you buy or build sitting on the bench with a specification sheet. Here, the random number generator is a black hole, not metaphorically. The physical process that determined which question the experiment asked was matter, falling into a supermassive black hole in the early universe, and the specification sheet for that component is cosmology. There is no other experiment I know of where the apparatus diagram would sensibly include an object 12 billion light-years away. So what does that actually buy you? It means that if you want to rescue Einstein's picture, by supposing that the settings and the particles were secretly correlated, that correlation must have been established at least 7.8 billion years before the experiment took place. It cannot have been arranged in the laboratory. It cannot have been arranged on Earth. It cannot have been arranged in the solar system because there was no solar system. Whatever did the arranging did it when the universe was under half its present age, and it did it in a way that anticipated an experiment that would be performed on a specific volcanic island by a specific group of people who would not exist for another 4.5 billion years. That is what physicists mean when they say a conspiracy becomes implausible. It does not become impossible. It becomes the kind of thing you have to say out loud to notice how much you are asking for. Now, and this matters, because it is the difference between the actual science and the version that circulates, the team did not claim to have closed the loophole. Read the paper. Read any interview any of them gave. They are precise about it every time. They say they have constrained it. They have pushed any possible correlation back to a specific and enormous distance in the past, and left open only the fraction of cosmic history before that point. David Kaiser, one of the principal investigators, is worth knowing about here because he is a historian of science as well as a physicist. He has written at length about how the foundations of quantum mechanics were pushed to the edge of respectability for decades, how a generation of physicists learned to say shut up and calculate, and how the people who kept asking what the equations meant were quietly filtered out of the profession. He is one of the people who dragged the subject back, and then he went and did the experiment. They had reached back 7.8 billion years to borrow a decision, and a gap remained, which raises the question that the rest of this video exists to answer. If you can push the problem back almost to the beginning of everything, why can you not push it all the way? Part 10. The wall that is not made of technology. The obvious next move, once you have used quasars, is to go older, and there is an older source. There is the oldest one there is. About 380,000 years after the beginning, the universe cooled just enough for atoms to hold together, and the fog of charged particles that had been scattering light in every direction suddenly cleared. The light released at that moment has been travelling ever since, and it is still arriving from every direction in every part of the sky. We call it the cosmic microwave background. It is the oldest light in existence, and there is a proposal in the literature to use it as the setting source for a Bell test. If somebody builds that, the conspiracy gets pushed back to within a few 100,000 years of the beginning of everything. That is, in percentage terms, essentially the whole way. It is not all the way. And here is where the story stops being about equipment. Everything in the observable universe shares a causal past. That is not a philosophical position. It is what the standard cosmological model says. Trace any two objects backward far enough and their histories converge. The quasar whose light set your detector angle, and the crystal in your laboratory that produced the entangled photon, are made of matter that was in causal contact at the beginning. Not close, in contact. There is no object anywhere in the universe that is causally disconnected from any other object, because there is no such thing as a causally disconnected object in a universe with a common origin. There is a subtlety here that is worth getting right, because people sometimes object at this point that inflation or the horizon problem changes the picture. It does not, and if anything, it makes it worse. In the standard cosmological story, the early universe underwent a period of extremely rapid expansion, and one of the reasons we believe that is precisely that regions of the sky, which should never have been in contact, are at the same temperature to within a few parts in 100,000. In other words, the evidence for inflation is that the universe is more causally connected in its past than the naive geometry suggests. If you are hoping to find two things in the sky that genuinely never shared a history, the cosmology is not on your side, which means the freedom of choice loophole can be made arbitrarily small and can never be made zero. Let me put you inside that, because the shape of it is the point. Imagine you are able to keep improving the experiment without limit. Start where we are. Your settings come from quasars 7.8 billion years back. Behind you, the window in which a conspiracy could have been arranged stretches from the Big Bang up to that moment, a few billion years wide. Now improve it. Use the cosmic microwave background, and the window narrows to a few 100,000 years. Improve it again somehow. Find a source of decisions from 100 years after the beginning, from a year after, from a second after. The window narrows and narrows. You can feel yourself closing on it. Every improvement takes a real bite, and the window keeps getting thinner, and it does not close, because no matter how far back you push, there is always a moment before that one, and everything you are using came out of it. You're walking toward a wall that recedes exactly as fast as you approach, and the gap between you and it never becomes nothing. It becomes small. It stays. That is not a technology problem. There is no detector, no telescope, no budget, no century of engineering that fixes it. It is a structural feature of doing science from inside a universe that had a beginning, which is the only place any of us has ever done science from. I want to be careful not to overstate what this means, because there is a version of this argument that slides into mysticism, and I have no interest in taking you there. Nobody is claiming that the shared past actually did arrange the correlations. There is no evidence for that whatsoever, and the overwhelming majority of working physicists consider it wildly implausible. What is being said is narrower and I think more interesting, that the possibility cannot be ruled out by measurement, in principle, ever, by anyone. That is a claim about the limits of a method, not a claim about what the universe is doing. Physics is extremely good at telling you which possibilities are excluded by data. This is one of the very few places where it can tell you that a possibility will never be excluded by data, no matter how much data you gather. So the list of ways to be wrong, that beautiful, honest catalogue that the field wrote out for itself and then spent 50 years working through, turns out to have one permanent entry. 4 items were engineering. They got crossed off at enormous cost by people who deserve every prize they were given, and several they were not. The 5th item was never an engineering problem. It has been sitting there since 1964, and it will be sitting there in 100 years, and the reason has nothing to do with how good we get at building things. Think about how unusual that is. In almost every other part of science, when you identify a source of possible error, the question is how much time and money it will take to eliminate it. The answer might be decades. It might be a facility that does not exist. But the shape of the solution is visible. Here, for the first time in this story, we have hit something where the answer is not later. The answer is no. The 3rd assumption is the only one left. And notice what it is, now that everything else has been cleared away from around it. It is not a statement about detectors or distances or timing windows. It is a statement about whoever is standing at the apparatus with a hand on the dial. It says, assume that person's choice came from somewhere outside all of this. For most of the last 60 years, that line has been read as housekeeping, a technicality, the small print at the bottom of the proof. It has been waved through in every textbook, mentioned once in every review article, and skipped entirely in every documentary. It is the flaw. Everything we have talked about tonight, Berkeley, Orsay, Innsbruck, Delft, Boulder, Vienna, 100,000 people on a Wednesday, a photon from a black hole 12 billion years ago, is standing on it. Every one of those experiments needed it to be true before it could conclude anything at all. Not one of them tested it. Not one of them could have. And there is one more turn of the screw, which I have been saving. Suppose you decided to test the 3rd assumption directly, to design an experiment whose outcome would tell you whether the experimenter's choices were free. Think for a moment about how you would read the result. You would look at your data, see a correlation between what you chose and what came out, and conclude something from it. But that inference only works if your choices were independent of the thing you were measuring. You would have to assume the very thing you were trying to establish in order to be allowed to conclude it. The instrument cannot be turned on itself, not because we have not built the right one yet, because of what it is made of. So what exactly were those machines measuring? That is the question, and I am not going to answer it yet, because there is one more thing you need first. There is a way out of all this. It has been sitting there the whole time. It is taken seriously by at least one Nobel laureate, and the person who explained it most clearly was the man who wrote the theorem in the first place. Part 11. The Escape Hatch. Bell left open. There is a position in this field with a terrible name and a worse reputation, and it deserves better than both. It is called superdeterminism. Before I tell you what it says, let me tell you what it does not say, because the caricature has almost entirely replaced the thing itself. Superdeterminism is not the claim that the universe is conspiring to fool physicists. It is not a claim that particles know what you're about to do. It is not a claim that there is some intelligence arranging events behind the scenes. Every one of those descriptions circulates, and every one of them is wrong. What it says is this. The 3rd assumption is false. Measurement settings and hidden variables are correlated, not because anything travels between them, not because anything plots, but because both of them are consequences of the same physical law acting on the same initial conditions. In a fully deterministic universe with a single origin, the state of your random number generator and the state of the particle in your apparatus are not 2 independent things. They are 2 outcomes of one process. Assuming they are independent is a convenience. Drop it, and Bell's theorem simply does not apply, and you can keep locality, and you can keep pre-existing properties, and nothing has to be spooky at all. That is the entire position. It is not exotic. It is the observation that one of the 3 premises might be the one that fails. Now let me tell you who said it first in public, and this is the moment I've been building toward all night. In 1985, John Bell sat down with the physicist and broadcaster Paul Davies for a radio interview. Davies asked him about determinism and the assumptions behind his theorem, and Bell answered directly. He said that there is a way out, a way to escape the conclusion of faster-than-light influences, and that it is to accept an absolutely determined universe in which everything, including the behavior of the experimenter, is fixed. In such a world, he said, the difficulty simply disappears. There is no need for anything to be signalled from one detector to the other, because the universe already knows what will be measured at both ends. It knew all along. And then he said the part that I think about more than almost anything else in this subject. He said that apparent free will can be a consequence of a completely deterministic world, and that in such a world, what we call our freedom to choose is an illusion, but a very good one. The man who wrote the theorem, the man who defined the three assumptions, the man who understood better than any living person exactly what his own result did and did not establish. He was asked what the escape route was, and he said, without hedging, that the escape route is that you were never free to choose in the first place. He did not say it to be provocative. He was not a provocative person. He said it because it was true, and because he was the kind of scientist who says the inconvenient thing out loud, even when it undermines the significance of his own most famous work. In talks and essays across the following years, he kept returning to it, turning it over, never quite able to leave it alone and never willing to pretend it was not there. It is worth understanding why the position gets the treatment it does, because the sociology here is unusually visible. When a physicist encounters superdeterminism for the first time, the reaction is almost always immediate and dismissive, and the dismissal usually takes one of two forms. The first is that it requires a fine-tuned conspiracy of initial conditions so absurd that no serious person could accept it. The second is that it is unfalsifiable and therefore not science. Both objections have been answered in the literature at length, and whether you find the answers convincing is a matter for you, but what is striking is how rarely the answers get engaged with at all. Hossenfelder has made this point sharply and repeatedly. The field is behaving unusually here, dismissing a technical position without reading the technical arguments, which is not how it behaves about anything else. I raise this not to advocate for the position, but because a story about a field that spent 50 years auditing its own possible errors ought to be honest about the one error it declines to audit. There is a detail in that interview I find almost unbearably characteristic of him. He did not present this as a defense of determinism. He was not arguing for it. He was answering a question about what his own theorem left open, and he answered it completely, including the part that made his result less dramatic than everyone wanted it to be. There is a version of John Bell who says nothing about this, and lets the world enjoy the spooky story. That version would have been more famous and less useful. So who works on this seriously now? The most prominent name is Gerard 't Hooft, who won the Nobel Prize in 1999 for work on the mathematical structure of the electroweak interaction. He is not a crank and nobody thinks he is. In 2016, he published a book-length treatment called The Cellular Automaton Interpretation of Quantum Mechanics, arguing that at the smallest scale the universe is a deterministic automaton, a set of simple rules updating a state, rather like Conway's game of life as it happens, and that quantum mechanics is a statistical description of that underlying machinery, rather than a fundamental account of it. He has argued, repeatedly and with some visible frustration, that calling this a conspiracy misunderstands the proposal. A law of nature that restricts which states of the universe are possible is not a conspiracy. Conservation of energy restricts which states are possible. Nobody calls that a plot. It also helps to see how small the required correlation actually is, because the word conspiracy conjures something enormous. Nobody is proposing that the universe arrange for a particular graduate student to be born. The technical requirement is far narrower, that the variables determining the measurement setting and the variables determining the particle's response are not statistically independent, that there is some correlation between them, however slight, in the specific moments when a Bell test is being run. Various authors have argued that the degree of correlation needed is surprisingly modest, and that the intuition of a vast conspiracy comes from imagining the wrong thing. Whether that defense works is genuinely contested, but it is a quantitative argument in the literature, not a hand wave, and it is a different claim from the one the caricature attacks. I should note one more thing about Hooft's version, because it makes the stakes concrete. In his picture, the states we describe with quantum superpositions are not physically real superpositions at all. They are our statistical bookkeeping over an underlying set of definite states he calls ontological. The equations of quantum mechanics come out right, because they are the correct statistics for that underlying machinery, but the famous strangeness, the cat both alive and dead, the particle in two places, is an artifact of describing a deterministic system with incomplete information. He has been working on this for well over a decade, and the main technical difficulty is not philosophical. It is that nobody, including him, has been able to build a version of the automaton that reproduces the full structure of the standard model. He says so himself. The other significant program is a paper published in Frontiers in Physics in 2020 by Sabine Hossenfelder and Tim Palmer, titled Rethinking Superdeterminism. Their argument is that the standard objections to the position are much weaker than the field believes, that most physicists dismiss it without having read the technical literature, and, crucially, that it makes predictions you could actually go and test. Specifically, they argue that if there is an underlying hidden state that needs time to reset between measurements, then Bell test correlations should show measurable deviations when you repeat measurements very rapidly, or at very low temperatures where the state evolves slowly. That is a real experimental proposal. It has not been definitively performed. Palmer has his own version, which I find genuinely beautiful even if I do not know whether it is true. He calls it invariant set theory, and it borrows from chaos theory. The idea is that the possible states of the universe form a fractal set, an intricate, infinitely detailed structure, and that the universe's history is a trajectory on that set. Now, the crucial move, a counterfactual measurement, the one you did not perform, corresponds to a point that is not on the set. It is not that the answer is hidden from you. It is that the question has no answer, because the state you are describing is not one the universe can be in. The road you did not take does not exist as a road. There are neighbours to this position worth naming quickly. Retrocausal interpretations hold that future measurement settings influence the past state of the particles, which preserves the third assumption, but sacrifices a fixed direction for causation, and which remains a small program with no experimental support. And some authors distinguish superdeterminism proper from a weaker cousin sometimes called supermeasuredness, where only the settings are correlated with the particle state rather than every event in cosmic history being locked together. I want to be honest about where all this sits. Superdeterminism is a minority position. Most physicists find it unattractive, and their reasons are not merely aesthetic, as we are about to see. It has produced no confirmed prediction. It is not the consensus, and I am not telling you it is right. But it is the only surviving way to keep Einstein's picture of the world after everything we have watched tonight. Every other route was closed by an experiment. This one cannot be closed by an experiment ever, for the reasons we just walked through. There is one more thing to say about how this position feels from the inside, because I think people expect it to feel bleak and it does not. Quite. Under superdeterminism, the world is local. Nothing reaches across space instantaneously. Particles have definite properties whether or not anybody looks. The universe is mechanical, orderly, and entirely comprehensible in the way a 19th century physicist would have wanted it to be. The people drawn to this position are not drawn to it by a taste for fatalism. They are drawn to it because it is the only route back to a universe that behaves itself. The price is paid somewhere else entirely, and where it is paid is the subject of the next part. And it costs something. It costs a great deal more than free will. Part 12. What it would cost. Anton Zeilinger, who shared the 2022 Nobel Prize and who was in the room for several of the experiments we have discussed, put the objection to superdeterminism in a single sentence, and it is the sentence that stops most physicists cold. He said that we always have the freedom to choose which measurement to perform, and that if this were not true, it would make no sense to ask nature questions in an experiment at all. Follow that through, because it goes further than it first appears. The experimental method has one basic move. You change one thing and watch what happens. You compare a group where you intervened against a group where you did not, and you attribute the difference to your intervention. That inference is the engine of every result humanity has ever produced by controlled experiment, and it runs on exactly one assumption, that your choice of what to change was not itself correlated with the thing you were measuring. If that assumption can fail, if the universe can quietly correlate what you decided to do with the system you decided to do it to, then the inference does not work. Not in quantum optics. Anywhere. A clinical trial for a new medication rests on it. So does every particle collider result, every agricultural field trial, every psychology experiment, every test of a bridge design. The correlation would not have to be large or malicious. It would only have to be there, So superdeterminism does not merely cost you your sense that you could have had toast instead. It costs you the method that discovered superdeterminism was a possibility in the first place. You're using a tool to argue that the tool does not work, and if you succeed, you cannot trust the argument. That is not a refutation. Let me be careful. A position is not false because accepting it would be inconvenient for us, and several people have made exactly that point in response to Zeilinger. The universe is not obliged to leave our epistemology intact, but it does explain why the field reacts the way it does, and it makes the shape of the trap visible. Now, I have been talking about physics all night, and I owe you a brief detour, because there is a second scientific attack on free will that most people have heard of, and it would be strange to leave it out. In 1983, a physiologist named Benjamin Libet published a set of experiments in which people were asked to flex a wrist whenever they felt like it, and to note the position of a dot on a clock face at the moment they became aware of the urge. Libet measured electrical activity in the brain at the same time, and found a signal, the readiness potential, beginning around 550 milliseconds before the movement, and crucially, several hundred milliseconds before the person reported being aware of deciding. The brain, it seemed, had started the action before the person knew about it. In 2008, a group led by John Dylan Haynes pushed this further using brain imaging, reporting that patterns of activity could predict which of two buttons a subject would press up to 10 seconds in advance, though at an accuracy of only around 60%, which is barely better than a coin. Libet himself, incidentally, did not think he had abolished free will, and it irritated him that people said he had. He argued that the readiness potential started the process, but that a person retained the ability to cancel the action in the last fraction of a second. He called it the veto, and some people have called it free won't, which is a better joke than it deserves to be. Whether that veto is itself preceded by its own unconscious signal is exactly the objection you would expect, and it was raised immediately. For a long time that was reported as neuroscience having settled the matter. It has not aged that way. In 2012, Aaron Scherger and colleagues offered a reinterpretation that has held up rather well, that the readiness potential may not be a decision at all, but ordinary neural noise drifting up and down, with the action triggered when the noise happens to cross a threshold. On that reading, the signal you are seeing before the choice is not the brain deciding early. It is the brain fluctuating as it always does, and the moment of action being the moment the fluctuation got big enough. The debate is very much alive. It is also worth noticing how different the two attacks are in what they would even establish. The neuroscience, at its most aggressive, tells you that your conscious sense of authoring a decision arrives after the process has begun, which is interesting and possibly humbling, but is compatible with the decision still being yours in every sense that matters, because you are not only your conscious narration. The physics is not making a claim about consciousness at all. It is asking whether the future is fixed. These are two genuinely different questions that get filed under the same heading, and a great deal of confused writing comes from sliding between them. I flag that strand only to set it beside the other one. It is a different kind of claim, about brains rather than about the structure of physical law, and notice where it ends up, unresolved, contested, and considerably more modest than its reputation. Both of the great scientific assaults on free will arrive at the same place, which is not a verdict. There is a broader lesson buried in that, and it is one of the reasons I wanted to make this video. In the popular telling, science keeps delivering verdicts about human beings. You are a machine, your choices are illusions, your sense of self is a story. In the actual literature, the picture is much less settled and much more careful. The strongest claims tend to live in the summaries, not in the papers. Go and read what the researchers themselves wrote in the discussion sections, where they list what their work does not show, and you will find a very different tone from the one that reaches you. And there is one more thing I have to close off before the end, because I promised you I would. Many people, on hearing all this, reach for quantum randomness as the rescue. If the electron's answer is genuinely undetermined, if the universe really does throw fresh dice, then the future is open, and surely that is where your freedom lives. It does not work, and philosophers have been pointing this out patiently for decades. Suppose the decision you made this morning was produced by a genuinely random quantum event somewhere in your nervous system. In what sense was that your decision? A choice made by a coin flip inside a neuron is not more yours than a choice made by a chain of causes stretching back to the Big Bang. It is arguably less yours because at least the deterministic version was produced by your history, your memories, your character. Randomness does not deliver agency. It delivers noise. If you were hoping quantum mechanics would hand you back your freedom, it does not have it either. And while we are here, let me leave you with one small piece of unfinished business that I find quietly delightful. Remember that number, the ceiling of 2 for a pre-printed universe, and 2.828 for quantum mechanics. It turns out that if the only rule you impose is that no information may travel faster than light, the mathematics permits correlations all the way up to 4. There is nothing in relativity that forbids it. Physicists have even given a name to the hypothetical devices that would produce it. They would not violate causality. They would not let you send a message. They are perfectly consistent with everything we know about space-time. The universe stops at 2.828 anyway. Nobody knows why. It is an open question, sitting right beside the most precisely tested result in this entire story, and it is a useful reminder before we reach the end. Even in the corner of physics where we have measured most carefully and argued most fiercely, we do not know why the numbers are the numbers. Which brings us finally to what physics actually found when it ran its experiment on free will. Part 13. What physics actually found. So let me answer the question I have been holding back all night. First, plainly, what the experiments established. The world cannot be described by a theory that is all three of these things at once: local, carrying pre-existing definite outcomes, and operating on freely chosen settings. At least one of the three has to go. That is not an interpretation, and it is not a philosophy. It is a theorem plus 70 years of data, and it is as solid as anything in modern physics. Second, plainly, what the experiments did not establish. Which one goes? Everything you have ever heard about what these results mean is a choice about which of the three to sacrifice. The mainstream gives up locality and definite outcomes, and keeps the freedom of choice. The superdeterminists give up the freedom of choice and keep the rest. Both are consistent with every measurement ever performed. The data does not adjudicate between them, and anyone who tells you it does has stopped reporting and started advocating. But that is not the answer. That is just the honest version of the summary. Here is the answer. Go back to the beginning of tonight. In 1935, the question was whether the world is the kind of place where things are decided in advance, whether when that particle gave its answer it could have done otherwise. That is the phrase we started with. It is the plainest possible statement of what everybody was arguing about. And for 13 chapters, you have watched physicists build machines to answer it. Calcium atoms in a Berkeley basement, ultrasonic switches in Orsay, diamonds a kilometre apart in Delft, nanowires in Vienna, 100,000 strangers on a Wednesday in November, light from a black hole that has been travelling since before this planet had a surface. Not one of those machines tested whether anyone could have done otherwise. Every single one of them assumed it. That is the third assumption. That is the fifth item on the list of ways to be wrong. It was there in Bell's paper in 1964, written down in the same handwriting as the other two, and for 60 years it has been read as small print, a housekeeping condition, waved through in the setup, skipped in the summaries. And when everything else was finally cleared away by 50 years of ferociously good engineering, it turned out not to be small print at all. It is the flaw. It is what all of it is standing on. The phrase flips, and I want you to feel it flip. For 13 chapters, you've been assuming that could have done otherwise was the question these experiments were asking. It was never the question. It was the premise. It was what had to be true before any of those machines could tell you anything at all. So, physics ran an experiment on free will. What did it find? It found that free will is not on the other side of the apparatus. It is holding the apparatus. And that is the unsettling part. Not a verdict about you, but a limit on what verdicts are possible. The most rigorous method our species has ever built, the one that gave us everything from the age of the universe to the medicine in your cabinet, has a load-bearing beam at its foundation that it is structurally incapable of inspecting. Not currently incapable. And if that beam is rotten, everything the method has ever told us goes down with it, including, in a final piece of symmetry that I still find funny in a bleak sort of way, the results of the very experiments that revealed the beam was there. I want to head off one reading of this before it takes hold, because it is the reading that would make the whole thing useless. None of this is an argument that the experiments were pointless, or that we learned nothing. We learned an enormous amount. We learned that a specific, natural, extremely reasonable picture of the world, the one Einstein preferred, the one most people carry around without examining it, cannot be right unless you are willing to pay a price somewhere. That is a real discovery about reality, and it took 70 years and several Nobel Prizes to establish it, and it stands. What has been revealed is not that the knowledge is fake, it is that the knowledge has a shape, and the shape has an edge, and the edge is in a place nobody expected to find it. Most limits in science are out at the frontier. The smallest scale we can probe, the earliest moment we can see. This one is not at the frontier. It is underneath the floorboards, in the part of the building nobody inspects because it holds everything up. Science needs you to be free. It cannot check whether you are, it has never been able to, and it never will be, and it has been quietly getting on with things anyway for 400 years. There is a symmetry here I keep returning to. Conway and Koshin proved that your freedom and the electrons are the same question. The experimental campaign then spent decades demonstrating that the electron's answer is not written down in advance, provided your choices are not written down in advance either. Read those two results together and something odd emerges. Physics has not been able to tell you whether you are free, but it has established as firmly as it establishes anything that you and the smallest constituents of the world are in exactly the same position on that question. Whatever you are, the electron is. Whatever the electron is, you are. You're not a special exception standing outside the machinery, and you're not obviously part of it either. Nobody knows which, and the not knowing is shared all the way down. I do not find that as bleak as it sounds, and I want to tell you why before we finish. Because look at what those people did. They wrote out a list of the ways they might be wrong in public, and then they spent 5 decades crossing items off it at enormous personal cost. Clauser was told it would end his career and built it anyway, and then reported the answer he did not want. The Delft team sat in a room for 18 days to collect 245 events. Somebody worked out how to use a quasar as a component, and when they got to the last item and found it could not be closed, they did not quietly stop mentioning it. They wrote it into their own papers, in their own moment of triumph, and pointed at the thing they had not done. That is not a story about the limits of knowledge. That is a story about a particular kind of honesty that human beings turn out to be capable of, sustained across generations, mostly by people who never met each other. There is one more thing worth saying about the shape of that limit, because it is genuinely unusual, and I do not want it to slide past. Most of the time, when science runs into something it cannot determine, the honest description is that we do not know yet. The instrument is not sensitive enough. The sample is too small. The theory is not developed. Give it 30 years and a facility that does not exist yet, and it will probably fall. Almost every open question you have ever heard about is of that kind, and the history of the subject is a long record of questions like that falling one after another, usually faster than anyone predicted. This one is not of that kind. This is a case where you can prove from the structure of the situation itself that no future instrument helps. There is no 30 years. There is no facility. The obstacle is not that we are looking with insufficient resolution. It is that the act of looking has the assumption baked into it. That is a rare thing to be able to say, and it is the reason this particular corner of physics keeps drawing people back long after the experiments are finished, and it leaves us here. Tomorrow morning you will wake up and make somewhere in the region of several hundred decisions before lunch, most of them so small you will not notice making them, whether to get up now or in 10 minutes, which way to turn at the end of the road, whether to say the thing you were thinking or let it go. Nobody knows whether those are yours. What we do know is that the entire edifice of measured human knowledge, every instrument reading, every trial, every experiment on this or any other subject, is quietly betting that at least some of them are. 7.8 billion years of travelling light, 100,000 people trying their best to be unpredictable on a Wednesday, and a list of ways to be wrong with one item that will never be crossed off. The universe has not told us whether you are free. It has only told us that it will not be answering that question, and that we will have to keep asking it anyway.